statements, propositions, sentences that are true or false, but not both. That's kind of an assumption that we have to make, that at least when we get into what we call propositional logic. I mean, that's really where we kind of spend most of our time, because in mathematical sense, we don't really deal too much with the gray areas, like kind of true, sometimes true. It's usually true or false, right? There are the rare circumstances where you have some sort of overlap, where something can be true under certain circumstances and false under other circumstances. But that's still propositional in the sense that depending on what those circumstances are, you would make a statement, a definitive statement of true or false, right? We tend to stay away from the opinion-based stuff, right? So the president is effective, true or false? I mean, aside from that just being a dangerous question in general, because depending on who the audience is, it could be, what do the kids call it? Triggering. The adults call it polarizing, but it's really just, it's opinion based, so that's why they do things like opinion polls, right? And data collection related to that, because it's not something that you can just pin down to true or false. And a lot of concepts in statistics, they try to determine truth value based off of something that could be considered opinion based, based off of data collection, right? That's not what we're going to do, because we're just trying to find the intersection between logic and geometry, so that's true or false. It's not like, is it a square? Well, in my opinion, no, that's not how it works. It's what are the circumstances surrounding a geometric figure being a square? Does it meet those requirements? Yes, then it's a square. No, then it's not a square. Does it meet some of them? Then it might be a square, right? But it might not be a square, right? But if we follow that path, or the line of reasoning, a pathway, we can make a determination of whether the geometric figure is a square. There is a true or false at the end of each pathway. It's just a matter of going down that pathway, right? In order to do that, we have to address certain logical connectives. We have the conjunction, disjunction, and the implication, right? The conjunction and the disjunction are straightforward enough. The conjunction is very straightforward. The disjunction is, I'll call it straightforward with a twist, right? Which of course makes it not straightforward. Now, there's like one little component of it that makes it seem a little bit weird, but the very strange one is implication. So that requires a little bit more explanation. You can kind of tell based off of the length of the definitions which one is the most complicated one. But the conjunction is an and, right? Any and in a sentence is known as a conjunction, right? We use a upside down V symbol, an almost capital A symbol, whatever you want to call it, kind of a triangle, but then the or symbol, the disjunction, is also kind of a triangle. But most people are comfortable just saying, oh, it's the one that looks like a V, right? But yeah, the conjunction is the and, right? And so only if both values of P and Q are true does the expression evaluate to be true, otherwise it's false, right? And so, I mean, there are examples that you can, you can just Google it, but I mean, this is a situation or circumstance, or whatever the right word is, where you can just kind of think about it for a second and see that this sentence makes perfect sense. Only if, grammatically it might be a little iffy, but only if both values of P and Q are true does the expression evaluate to be true. Evaluate to be true. So if I give you an example, I'm saying I'm wearing a red shirt and blue shorts. I mean, I'm saying that I'm wearing both the red shirt and the blue shorts. So if I come walking in with the green shirt, then I'm lying, right? So AKA false. It's a false statement, and just thinking about a situation where high school students, they're like, okay, everybody's gonna wear a red shirt today, right? And we're gonna dress up for Spirit Week or something like that. So red shirt and I guess blue shorts. I mean, I already used it. So red shirt and blue shorts. Right? Everybody's gonna do that. And then you come in, you're wearing your red shirt and blue shorts. So a true for you. You're true. Right? Your friend comes in with red shirt and blue shorts. True for your friend. Another friend didn't get the memo. Red shirt and blue pants. Not shorts. So false. Didn't meet the criteria that was stated. Right. So, and actually, you can kind of even think about that as a kind of a triple conjunction, or triple component conjunction. It's really a double conjunction because it's two ands. Because if I say, well, actually, even four components. If I say you're wearing, I'll make a little note of it here. So, example, red shirt and I'll actually just write it out now. Blue shorts. I think my pen is dying. I charged it for a while today, though. I think it might be just skipping. All right, red shirt and blue shorts. All right, so if both of these conditions are not met, then the sentence is false. All right, so the elements that make up your conjunction need to be propositional in the sense that they have to have a truth value. There's no gray area. It's either true or false, right? There must be some way of evaluating, right? So, but what I was getting at here is that when I say that there's a red shirt and blue shorts, this could also be stated as, so AKA red and shirt and blue and shorts. All right. So where you're wearing a shirt that is red and blue shorts. So shorts that are also blue. Right. The reason I'm mentioning this is because maybe the person that came into school got the memo. They knew they had to wear a shirt, shorts. One of them was red and the other was blue, but they didn't know that it had to be the red shirt and the blue shorts. Right. So it's a requirement that it needed to be red and a shirt at the same time, and also blue while also being a pair of shorts. Right. So kind of a tricky thing when you break it down to its most basic elements. A lot of the things that we talked about in everyday life, they can be really complicated when you really, really think about it. Right. So I am going to get in my car and drive to work. Right. So you think about all the things that have to go into that idea in order for it to be something that could actually happen. So I have to be a person, which I guess is easy enough, right? And I have to have a car. I have to then get in that car and then drive to work. So a lot of different base components that make the whole thing up. Now, when it comes to geometry, there's a lot of base components that make up situations too. But we'll get into that as we go forward, because when I don't want to lead off of that, because if I tell you that a square is a geometric figure that has four sides that are all of equal length and has four angles that are all of equal size, that's five components of an and state, right? So there's a lot going on there, and we'd have to make sure that every one of those things are true. And there are even other contributing factors to determine what makes something a square. So there's a lot, like I said, a lot going on. A disjunction denoted by the or symbol, right? The V, right? Or the upside down or the reflection of the and symbol, P or Q. right? P represents some statement, Q represents some other statement, right? As long as one of the values is true, the entire expression is true, right? So if I say that I'm wearing red shirt or blue shorts, then as long as I've satisfied one of those conditions, I'm telling the truth. The problem with with a disjunction and the aspect of it that makes it confusing to people is that it makes it seem like a choice, right? So if I said I'm wearing a red shirt or blue shorts, and then I walk in wearing both a red shirt and blue shorts, and you'd be like, hey, you said you were going to wear a red shirt or blue shorts. You didn't say you were going to wear both. Well, the or the disjunction allows for the both to be a possible consequence. Right? So if I tell you, I mean, just thinking about it in a mathematical sense, if I tell you that, I'll just keep it simple, X is 2 or 3, right? I'm not telling you that it's a choice between 2 or 3. I'm saying if you selected 2 or 3, you're right. Right? Just think about it like a multiple choice question. Right? If you select choice A or C or D, you are wrong. Right? Any of those. Now, if you somehow selected all of them, you'd be really wrong. Which I suppose would be possible. I mean, it would be foolish, but it would be possible. But any of those would consist of the wrong answer. So that would allow the disjunction to encompass the entire set. All right. I'll get into more specific cases of this down the line, especially symbolic notation, because believe it or not, this is the kind of thing that actually gets easier when you get into the symbolic notation. When you start thinking about it contextually, it becomes a little bit more mind-bending. The implication, which is the mind-bendiest of them all, right, denoted by the sideways arrow symbol. P sideways arrow Q is P implies Q, right? Or you could say if P then Q, right? Where P is the premise and Q is the conclusion. Sorry, right? So I don't think I wrote any of that there. So, oh, actually, I said if P then Q right there, so that's good. But P is also known as the premise. That's not a P. Kind of wrote it there. It's just sort of buried in my notation, my words. Q is the conclusion. All right. So I guess there's a little typo here. I forgot to write something there. There should be an A here. And so a few examples here. If my bread is green, then I will not eat it. I mean, I think that makes sense. If they like, I wouldn't want to eat green bread. So, I mean, it's an assumption that it's molded and past the expiration date. One usually coincides with the other, but you never know. Right. So the thing is, and I'll just read the blurb here. If the bread is not green, then it does not guarantee that I will not eat it. Right. So that's the thing. We know what will happen if the bread is green. We don't know what's going to happen under any other circumstance. Right. So that's where the implication gets tricky. Right. Because if you're given a premise and you satisfy that premise, then that's the obvious answer. You know, so if I tell you that the bread is green, if the bread is green, then I will not eat it. Right? That's the promise I'm making. That's the conditional sentence. I mean, it's really the basis of, you know, contract language. Everything in a contract is conditional. Right? There are some statements right? In a contract, like if you're contracted to work, like certain things like this is what your rate of pay will be. But there are other things that are conditional, like if you don't show up to work, you're fired, right? But if I do show up to work, does that mean I won't get fired? No, if I show up to work, there are some things that I can do while at work that could get me fired. There are some things that I might not do at work, even though I'm there, like, work that could also get me fired. Right. If I'm not living up to the conditions of the contract, then it's false. Right. But if I don't have any idea of what the circumstances would be if the premise is not met, then that's a different situation. Right. So, I have this whole blurb here about if you score a 90 or above in this class, then you'll get an A. Right. Seems reasonable. I mean, that's what the standard is. But what if I don't score 90 or above? What if I get an 88, but my teacher is really nice? I could still get an A. Right. So I didn't satisfy the premise, but the conclusion is still in play. It's still a possibility that I can get an A. Right. The only way that this becomes a violation is if you get 90 or above in the class and I don't give you an A. All right. So we think about false when it comes to, true versus false when it comes to an implication. The true is when the contract is satisfied. Right. False is when there's a violation in the contract. If there's ambiguity in the contract, then we still consider that a satisfaction. Right. So if I say, like, let's say, for example, I did not get, well, I'll just use the example that I gave before. I got an 85 in the class. So it's not true that I got a 90 or above in this class. But then my teacher was generous and gave me the A. All right. It's still a true sentence because my contract was fulfilled. Right. There's no violation in this contract. Right. That's what they call a loophole. All right. So I'll get to the symbolic notation in a second, but that's what really that boils down to. Right. So the biconditional, that's the weirdest one, because in terms of the way we would state it in a math class, like there's no legitimate expectation that anybody would use this verbiage in real life. But there are other ways of saying this in real life that get at the same idea, and that's when things get confusing. All right. So the double arrow, right, double sideways arrow, is read as if and only if. All right. So the phrase if and only if is abbreviated with IFF, so a second F on that. All right. So that's P implies Q and Q implies P, so both directions. I've never made a worksheet that I can't, or didn't make a typo on. This arrow should be the other way. All right. So I'm saying only when P is true, Q is true. All right. So the example, if and only if my alarm clock rings in the morning, then I will attend my morning class. And nobody speaks that way. All right. So, but it's kind of like if you, I don't know, emphasize certain parts of that expression, if and only if my alarm clock rings in the morning, then I will attend my morning class. Right? So that's kind of a little bit better way of kind of tying it together with the common vernacular. But it's more like the only way I'm going to class in the morning is if my alarm clock rings. I mean, the only way I can teach this class is if I can actually speak, for crying out loud. So, that's a more everyday way of explaining the same idea. It's still a biconditional, but there's really no indication of the word if in there, let alone if and only if. So making the connection between the everyday way of speaking and how we speak logically, and then therefore how we go about proving things geometrically, that could be kind of a bear, because what happens is, and this is why we're going over this, when I say prove that this geometric figure is a square, or explain why this geometric figure is a square, and students write it in their own way of kind of just speaking, oftentimes it's not logically sound. So the explanation's invalid, right? Because it doesn't follow the logic, right? And so if that happens, then, aside from it being wrong, like you will have not really gained anything from that discourse, right? So yeah, we want to make the connection between the formal logic and also the way everybody would normally say things, and really just kind of get at the idea of like what would be considered correct and what would be considered incorrect in the everyday way of saying things, not just the logic way of saying things, or the propositional logic way of saying things. So then you have that tilde symbol. That means not. That's probably the simplest part of this. Right? If you see a tilde, it means not, or it means the opposite. The opposite of whatever the statement is represented by the letter. Right? So if I say tilde P, I'm saying not P. If P is talking about, for example, I will wear a red shirt, then not P would represent I am not wearing a red shirt. Right? So that, like I said, that's the simplest thing. If you don't know the symbol, if you don't know the symbolism, nothing is simple. But that's as far as things go. That's not bad. Right. So a little kind of a cheat sheet here. So A and B. I switched to A and B's for some reason. I have no idea why. A or B. If A, then B. If A, then B, or if B, then A. Not A. Now the triple equal sign, the triple horizontal line here, kind of like an equal sign but with an extra bar. We talked about congruence. That's the equal sign with a little tilde over the top, right? But that means something different. That's congruent. This is saying is equal by definition, right? Or by rule, right? So when we say by definition, we're saying by rule. There are certain things that we know to be true. These are just facts of nature, things that you learn the rule, and it's like, why is it true? Because Pythagoras said so. That's why, and it's been proved over and over again. So, for example, you might have seen a squared plus b squared is equal to c squared. But it's really a squared plus b squared is equal by definition to c squared. All right. It's cumbersome to write the triple equal. You're doing it in an algebra class or computational skills class. If you had to write that triple equal sign every time, it'd be kind of a pain. Right. But when you're given a rule and it's been proved, it's a theorem, and it's a triple equal sign technically. And this whole unit is, well, the whole part of the unit is about technicality. All right. This one is kind of strange. Little equal sign with a vertical little hatch there. B is true in every structure in which A is true. All right. So that's basically saying if A is true, then B is true. Assuming we use A as the premise. Right. So if we know that A is true, then as a consequence, we can prove B to be true. All right. But that, we're a little bit away from that, because that one's the mind bendiest of all of them, I think. And you'll notice that the symbol here this little inconsistency here. It's got an equal sign with a vertical, and then here it's just a single. The symbols mean the same thing, right? So,
Professor,
yeah,
sorry, was that added? Because I can't find that on the sheet and I'm on page 2.
oh, it was added at some point. I just don't remember when. Let me take
The
a look.
notation, my page 2 starts with the tables. It doesn't have the notation.
So, okay, so you don't have the notation at the top. All right, it might not have refreshed. Let me. Okay, so we're going to learn about truth tables. Now, truth tables are ways of proving sentences to be either valid, unsatisfiable, as in a contradiction, or satisfiable, which means depending on the circumstances, it could either be true or false. Right? So, yeah, it's an acquired taste. As you can see, it looks fairly complicated, but we can use it to determine the truth or under what circumstances certain arguments are valid, right? And that's really what this comes down to, right? Determining the validity of certain arguments, right? So the first little table here, this is the conjunction P and Q. All right, now for the conjunction, this was stated on the previous page. So this is just going to be a fact at this point, right? So on the previous page, I was saying that the only way an and sentence can be true is if both parts are true, right? So this array of values here really just boils down to different possibilities if you have two sentences, right? So if I'm saying P represents the event or I guess I'll use event, that I'm wearing a red shirt, and Q is the event that I'm wearing blue shorts. It could be true that I'm wearing a red shirt and blue shorts. It could be true that I'm wearing a red shirt, but false that I'm wearing the blue shorts. It could be false that I'm wearing the red shirt, as in I'm wearing like some kind of green shirt or blue shirt or black shirt, whatever. But it could be true that I'm wearing the blue shorts, or maybe I'm neither wearing the red shirt nor the blue shorts. Right. So those are all the different ways that two statements in conjunction can have truth value. Right. They can either both be true, both be false, or some other mixture. Right. True, false, or false, true. Right. And the only way a conjunction sentence will ever be true is if both parts are true. Right. And so that goes back to what I was saying before. I know it's a lame example, but it's simple. I like going with the simple examples because the complicated ones are really, they start driving a little insane. But if red shirt, blue shorts, right? If I say that I am wearing, like it's an in-person class and I'm going to show up on next Wednesday, and I say I'll be wearing a red shirt and I'll be wearing blue shorts. Mark my words. And I walk in and I'm wearing a black shirt, but I'm wearing blue shorts. It's still false. I said I was going to wear a red shirt and blue shorts. I didn't satisfy the claim that I made. Right. Now, if I say that I'm going to wear a red shirt or blue shorts, then the only way I'm lying to you is if I'm neither wearing a red shirt nor blue shorts. Right. As long as I'm wearing at least one of those things, I'm telling the truth, right? If I happen to be wearing both the red shirt and the blue shorts, you're like, okay, that's overkill, but you didn't lie. I'm wearing a red shirt, but I decided to wear jeans. I'm still telling the truth. I'm not wearing the red shirt. I decided to wear a black sweater, but I'm wearing blue shorts for some reason. I'm not lying. I'm still telling the truth. Right. So these become givens, right? So this is just the explanation for it, but it's not like you have to invent this every time. We'll actually use this information in order to evaluate more complicated situations. So the implication, that's the one where we're talking about a contract and whether I've upheld the contract. All right. So implication, the if then, the blue shorts and red shirt here is a little trickier when it comes to an if then. If I'm wearing a red shirt, then I'm wearing blue shorts. It doesn't really sound like much of a contract. I like the if I go to work, then, or if I don't go to work, then I will get fired. Or if I get a 90 or above, then I will get an A. You know, those are more relatable. If I fill up my gas tank, or if I don't fill up my gas tank, my car will break down. Right. So any of those are kind of easier to sort of wrap your brain around. Right? Anything that is a condition that needs to be met, followed by the consequence for meeting or not meeting that condition. Right. So if I go with the grade one, if I get a 90 or above, then I get an A. Right. So I worked really hard. I got the 90. And then the teacher gave me an A. Contract upheld. All right. I worked really hard. I got a 99. Teacher did not give me an A for some reason. They hate me. The agreement was, if I get a 90 or better, 90 or above, I will get an A. I did my part. I got the 90 or above, but you didn't give me the A. That means that you lied. The contract has been violated. Right? Now, the grayer area here, but it still makes sense when you think about it. If, again, the initial implication is, if I get a 90 or above, I will get an A, then I will get an A. All right, so I get a 70, but the teacher gave me an A. All right, it's still true. It's still a true sentence. The contract has been upheld because I never said what would happen if you didn't get a 90 or above. I could still give you an A. I only said what would happen if you did get a 90 or above. All right. I said that I will give you an A if you got a 90 or above. You got a 90 or above. I didn't give you an A. That's a false. You didn't get a 90 or above, but I still gave you an A. I'm just a nice guy, but that has nothing to do with the contract. All right. So the contract hasn't been violated because it's not even in effect, because the premise hasn't been met. All right. And the same thing with false implies false. The contract is not violated because the premise hasn't been met. The contract isn't even in effect. All right. Now, the biconditional, is basically P then Q followed by Q then P in conjunction. The biconditional outcomes are TFFT, which we can now take as a rule, but it's satisfiable in the sense that it's not always true. It's only true if both parts are true or both parts are false. So looking at example 1, we have P implies Q. We have that up here, so we could just snag that. So TFTT. Then they're asking us to find Q implies P, which is just looking at the same connective, just in the reverse order. So we have true, then true, so it's going in this direction. True, then true is true, just like you see up here. False, then true
is going to be true. So that's this one. True then false, that's going to be false. That's this one here. And false then false gives a true. All right. The biconditional tells us that if the components that make up that biconditional are the same, the result is true. So that first one is true. Second one is false. Third one is false. Last one is true. So this is what we call satisfiable. And that is because it's sometimes true. It's able to be satisfied under certain conditions. Right? If that last column was all true, then it would be valid. It's always true. Unsatisfiable means that it could never be true. So same deal with the next one. I could just actually snag all this stuff right here and just bring it on down the line. All right, not P, then not Q. All right, so it might be worth your while to just come up with a little separate table here with all the not P's. So false, false, true, true. We're just taking the opposite of everything that's in the P column. Then false, true, false, true. And then following our rules for the conditional, true implies true is true. That's that last one there. So true. Then true implies false. I have that right here. That's false. False implies true. That's true. And false implies false is going to be true. All right. So same deal. We go on down the line. Anything that matches true, true is true. False, true is not. True, false is not. And true, true is true. So this is also satisfiable. All right. We are looking for some way to generalize this stuff. So we want to have circumstances that lead to what we call a tautology, which is the case where it's always valid. Right? So if I can come up with relationships that yield a column that's entirely made up of true values, then I'll have a relationship that I could use for substitutions and things like that. Right? So I have an extra row in this one for some reason, so we can get rid of that. All right, so true, true, false, false, true, false, true, false. All right, not Q. I mean, I included the columns here, so that should be a little helpful. All right, so not Q is false, true, false, true. Not P should be false, false, true, true. All right, so P implies Q. We've done that a few times now. Oops. True, false, true, true. Not Q implies not P. I could just grab that from here. All right, so that's going to be true, false, true, true. And now you can see for the last column, I have true for the first one because the two components that make up that biconditional, this one and this one, they're made up of the same ingredients. True then true is true, false then false is true. True then true is true, or really true if and only if true. And the same thing for the last one. All right, so this is valid, also known as a tautology. All right, that gives us logical equivalence. So, or logically equivalent. All right. Anytime you can equate two things in such a case that they're always going to give the same result no matter what you sub in, that's going to give us logical equivalence. All right. So I could say P implies Q is logically equivalent Equivant? No. To not Q implies not P. Right, there's other types of logically equivalent statements, and so we'll explore another one, and then I'll show you a whole list of them. All right, so in the next one, it's the same ingredients: true, true, false, false, true, false, true, false. I put a not P here, so it's false, false, true, true. All right, so for the OR, it's comparing these two columns. Now, OR is commutative. You can go in either order. So not P or Q versus Q or not P means the same thing. If you remember, the only time a false an OR statement is false is if both parts are false. So we're looking at true, false, true, true. And we know from having done this a bunch of times now, true, false, true, true is the or set of outcomes for the conditional. And the biconditional, oh, apologies, I should have a double-sided arrow. The biconditional is just really asking if these two things give the same truth values. They do. So this is a tautology. It's completely valid. It means that P implies Q is logically equivalent to not P or Q. Right. So now what we want to do is we want to be able to take this and convert it over into everyday language. Right? When you're evaluating the logic of a situation, there's usually a scenario involved, and maybe a legal contract or something like that, and you want to be able to assess its viability, determine really any kind of loopholes. Because when you're talking about a conditional, if this then that, I mentioned before that it's like a contract. So if the terms of the contract are met, what are the outcomes? Now the question would be, if the terms of the contract are not met, what are the outcomes? Right? So that's where that weird circumstance of true implies false being equal to false, that could create a loophole. All right, so I'm looking at this example here. Now, really, at this point, we're just taking sentences and putting them in symbolic form. And I'll talk to you a little bit more about laws of logic, and then we'll be able to apply the laws of logic to sentences that are in symbolic form, or that we put in symbolic form. So F represents I eat the right foods. S represents I get sick. All right, should be a little space here. If I eat the right foods, then I don't get sick. I don't get sick, or I don't eat the right foods. That's all I'm asking you to do at this point. All right. If Simone takes chorus is C, then she cannot take Spanish, so not S. If Simone takes Spanish, then she can not take chorus. All right. So we're going to talk about laws of logic. And really, at this point, it's just a matter of saying, here's a list of laws, because I don't expect you to memorize them. Here's a list of laws that we could use in certain conditions. All right, so you'll see the example that follows there, a solved example, and some keep in mind statements. But I think it's probably better for me to take you through an example or two directly. So I just noticed that there was a typo on page 4, the guided example. The therefore part of it should be, there's really no reference to a greenhouse effect in here. It's an old problem that I modified, and I forgot to change the last part. Therefore, the people will be afraid. All right. And that's the conclusion. That's to be proved. All right. So and it just taking it from the beginning, if we choose nuclear power, now in the solution I let N be we choose nuclear power, so N, then we increase the risk of a nuclear accident, which I called R, so that's where this first statement comes from. If there's a risk of a nuclear accident, so that's R, then the people will be afraid, which I called A. Apologies. And then the next statement was we choose nuclear power. So that I defined as N. So all three of these statements are accounted for. So what I did was I took, I kind of wrote it, what am I doing here? I took these two and I applied the law of syllogisms. All right, so when I say N implies R and R implies A, it's saying that I'm taking those two statements together and determining what the conclusion would be. Now, up in your table here, you see that there's one in item 14. P implies Q and Q implies R. Therefore, P implies R, or if and only if P implies R. They mean the same thing, all right? And so it's kind of like, I'll give a very simplistic example. If I drive to Syracuse, then I will drive to Buffalo. If I drive to Buffalo, then I will drive to Toronto. So wouldn't it make sense to say that if I drive to Syracuse, then I'm going to drive to Toronto? All right, so that's really, the idea of kind of cutting out the middleman. All right, that's what the law of syllogisms tells us. All right, so these two amount, wrong marker. These two amount to N implies A. Now, if I take that along with the N, this is what we call modus ponens. All right, so that's this item here. It's affirms by affirming. It's really just confirming the premise. If you get a 90 or above, then I give you an A for the course. And then I follow that up by saying, oh, look, you got a 90 or above. So if you get a 90 or above, then you get an A for the course. You got a 90 or above. Therefore, it makes sense that we would say that you get an A for the course. Coincidentally, that is what the conclusion would be here, the letter A. All right. So we would conclude A, which we defined as people will be afraid. So this is telling us that if we choose nuclear power, then people will be afraid. That's what this sentence is telling us, because we kind of cut out the middleman of the risk of a nuclear accident. And then we're confirming that we chose nuclear power. So you can believe. So you better believe that people will be afraid. All right. Now, I chose to do it in this order. You could take any sentence and pair it with any other sentence with a conjunction and apply a rule, which kind of makes things more complicated. But that's when, if you're talking about a legal contract, that's when you might have like loopholes in there where people just kind of play around with the phrasing of it in the hopes that you kind of miss a small detail. All right. So there is more than one possible route to the conclusion. The order of steps doesn't matter. The number of steps, if it takes you 20 steps to get to the answer versus 2, it's just a question of time. But it doesn't matter in terms of the logic of it. You can use premises to justify more than one step, and it's all right if you don't use any of the premises at all. All right, sometimes there's a extra statement in there that, it's kind of like a red herring. All right, so the examples that follow, we could do these a couple of different ways. One way would be to create a truth table. When we're asked to prove something, proving is looking for validity. All right, so that would mean that it's true in all cases, which can be done with a truth table. Now, in some situations, the scenario is more convoluted. Like you might have like 10 different sentences to make up your set of premises. If that's the case, then a truth table might not be the best approach. All right. So what I would do is try to use one of the laws of logic. And if I can't find that one that fits, then I'll use a truth table. Right. So prove Q implies P is logically equivalent to P or not Q. Well, that one looks pretty close to the implication identity. If it's an identity or a law, it's a rule. It's something that could be applied in all cases. It's confirmed. They are logically equivalent. All right. So implication identity. P implies Q is the same as not P or Q. All right. So what's happening here is we have Q implies P. Now, if I want to get this to fit this, I'd have to manipulate it using, we could use a bunch of different approaches, but I think the best way to do it is to kind of create a, call it a role reversal. Right? So I'm going to let this Q be equal to these P values. All right. So I'm going to replace the P's in my implication identity with Q's, and I'm going to replace the Q's in the implication identity with P. All right. So that's going to become, just through direct substitution, Q implies P if and only if the not stays put. I'm replacing the P with a Q, put it in parentheses just to kind of accentuate it, and then replace the Q with a P. So I have that. All right, so this is substitution. When we prove something, you need a justification for everything you do. All right, so we're applying the implication identity. You could say substitution into the implication identity, but substitution, as long as you indicate what the implication identity is, that's perfectly fine. All right, so Q implies P is the same as not Q or P. All right, which is this expression just reversed. All right, so P or not Q is the same as the not Q or P, and that's because of the commutative property. I mentioned that before, that the or sentence is commutative, meaning that you do it in either order, it means the same thing. All right. Now for number 2, you could look at this and apply a similar approach, or you can make a truth table. All right. So if you can find a rule that fits, then find the rule that fits and apply the rule. If not, a truth table would be the way to go. All right. Now this one happens to be the textbook case of De Morgan's laws. All right. So if you go back to the table here, so it definitely helps to have a look at this laws of logic table. So De Morgan's laws is telling you that if you negate an or sentence, it becomes an and with each component of that or sentence negated. Same idea with an and becoming an or. This is a very popular one. It's very, I'll say consistent with the law of double negation, because when you negate something, it becomes positive. So you'll see that, when we get into the example, that if I apply the De Morgan's laws, that any negatives will become positives and any positives become negatives. All right. So De Morgan's laws again. So De Morgan. All right, so if I negate P or Q, it'll become not P and not Q. All right, so I might want to try a substitution on that. And again, the other variation, I might be doing this in a reverse order, tongue twister. It's really not, I just got twisted up. So not P or not Q. All right, so depends on which one you want to start with. I'm going to start with this one here and apply this rule. All right, so I have not, and you kind of think about what the components are. This is a P. I mean, it says not P, but it's P in this form of the De Morgan's laws. All right, Q is what it is. So I could rewrite this as not, instead of P, I'll say not P or Q is going to be equal to not P and not Q. All right, so that's by substitution. Apologies. This never makes anybody feel good when you write it in the same size I'm writing it, and then you see me shrink it down to fit more stuff. That's unfortunate, but necessary. So substitution, and then not P, it becomes P, and not Q stays put, and that happens to be what we were looking at. So initially, I should say. And so what we have here by double negation, law of double negation, is we have a proof. We determined what we were trying to determine. We proved what was to be proved. So we could say QED. To represent that. All right. So again, a proof is really just making a statement and then justifying it until you get to whatever it is that you're trying to prove. All right. So for number 3, let F represent I eat the right foods. Let S represent I get sick. Prove that 2 compound sentences below are logically equivalent, or give a reason why they're not. If I eat the right foods, so F, then I don't get sick, so not S. I don't get sick, not S, or I don't eat the right foods, so not F. Right. Anytime I'm looking at a conditional followed by an or, I tend to think along the lines of the implication identity. All right. So this one actually may be slightly easier to follow because we're not overusing variables. All right. So the rule itself has P's and Q's in it, but my sentence here has F's and S's. All right. So I'm going to take F and replace the P in my implication identity with that. And then I'm going to take my not S and replace the Q with that. All right. So by the implication identity, I probably shouldn't use an arrow there because that'll get confusing. So by implication, this is going to become not F or, all right, so again, the not was built in there. I'm just replacing the P with an F. So, or the Q is replaced with a not S. All right, now if I just flip the order, so by commutative property, or commutative law, this would become not S or not F. It's just switching the 2 pieces around. All right. And so that's it. I just showed that this and this are the same thing. Right? So you could say, therefore, not F, F implies not S is the same as not S or not F, or you could say QED. As long as you have your justifications there, throwing in a QED is fine. It's just really me having an idea that you know that you've reached the end of the proof. M represents Michael likes math. S represents Michael likes science. Logically equivalent or not. Not true that that Michael likes both math and science. Michael does not like math, or Michael does not like science. All right. So again, De Morgan's laws. All right. I'll work with. Let me get rid of that highlighter there. The second variation of it, I'm going to replace the P with an M and the Q with an S. So each P gets replaced with an M. Let me just smidge this over. So by De Morgan, we would say not M and S would be equal to not M or not S. All right, equals. Jeez Louise. I mean, we sort of treat it the same way, but the proper logical notation is the biconditional. Okay, and so now a full-blown proof. So aside from, because I know people are concerned about, okay, so what of this stuff will be on the test? You could always look at the practice test to get an idea, because whatever I put on the practice test in order is going to be the type of question that you'll see on the unit test. Maybe on the practice test it'll be multiple choice, but on the actual test it'll be short answer. But you know, it's the same general theme, right? So you could always look there. But I can tell you right now, for logic, it's really about general rules. So having an understanding of these relationships, and also being able to complete one of these proofs. All right, one of these types of proofs. All right, all this stuff here is sort of foundational to get us to understand how to approach this type of thing. All right, now the notation could be a little convoluted, but the same idea holds. All right, you're going to apply a law, and when you actually tackle these problems on your own, you'll see that you're really just trying to find a rule that fits what you see on paper. And it is an acquired taste. You don't see it immediately all the time, but once you get a little experience, it becomes more obvious. Like, for example, we have our three premises. The first crazy one, the second one less crazy, and the third one is the simplest. Let me start off with the second and third set of premises here. All right. Now, you may not notice that is modus ponens, but let me show you modus ponens. P implies Q, and P is the same as just saying Q. All right. What that tells me is that if I have a contract, if this, then that. If I wear a t-shirt, then it must be fall. So then I tell you that I'm wearing a t-shirt, then you say, okay, well then it's fall. All right, that's what's happening here. I'm confirming the first piece. Another way of writing it would be to say P implies Q, then the P below it, and then we would conclude Q. All right, so let me match this with what I see here. All right, let P be equal to S or L, and let Q be equal to not G. So I would be saying S or L instead of the P implies Q. Well, the Q is not G, so let me get the not G in there. And then P again, so S or L. The result, if I follow this model, P implies Q, confirm the P, get the Q. P implies Q, confirm the P, get the Q. All right, so my first conclusion, not G, is by the modus ponens rule. All right, now that actually happens again, because if I look at, now let me move my box here. If I take this sentence and this sentence, you'll notice how the premise is confirmed, right? So this is P, this is Q, P again, P implies Q, confirm the P, get the Q. All right, so if you look in the next sentence here, that is whatever we had as Q. So we have modus ponens again to justify this sentence. But then we're kind of curious about, okay, well, how do we release the S implies G from this mess? All right, so for that, I'm going to look at, just take a close look at number 5. You see we have an or sentence there. All right, so now 4 and 5 have been proved. These are known to be true sentences now. All right, so we could use any of the premises and or the stuff that we proved to prove the stuff that comes along afterwards. All right, anytime I want to release a component from a sentence, all right, so we have the connective, we have the two statements, right? If I want to split the statement or the sentence up into statements by the connective, then and that connective is either an and or an or, I could use law of disjunctive inference. All right, law of disjunctive inference, if I have something like P or Q, all right, and then I tell you not P, then the result would have to be Q. All right, so this is the or instance, the real life or instance where it seems like a choice. All right, if I tell you I'm going to get my next car is either going to be a Toyota Tacoma or a Chevy Colorado. You know what? It's not going to be the Toyota Tacoma. Well, then it's going to be the Chevy Colorado. It's one or the other. It's not one. It must be the other. All right. Same idea goes for P or Q and not Q. Well, it's either P or Q. It's not Q, so it must be P. All right. So looking at this, I'll box it in so you know what this is. It's either G or S then G. Well, it's not G, so it must be S then G. So this is disjunctive inference. Abbreviations are fine as long as I know what the abbreviation is or represents. All right. So now we have S then G, but I want to somehow get a not S out of that. All right. There's also modus tollens. All right. So P implies Q. If I tell you not Q, therefore not P. Now this is a strange one because it's actually a contrapositive applied followed by modus ponens. So it's a shortcut that takes two different laws and merges them together. I'll just show you real quick. So if I were to take the contrapositive So I'll just say explanation. If I take the contrapositive of P then Q, that'd be not Q then not P, switch and negate. And then I bring down the not Q. Now I have a affirms by affirming a modus ponens. All right, so if it's not going to rain, then I'm not going to stay inside. Well, it's not going to rain. Well, then I'm not going to stay inside. You may not find it to be as valuable as I do to attach words to the symbols. When the symbols are given out of context, though, I find that it's a little easier to kind of imagine my own context and apply it rather than just going by the letters. All right, just going back to the if I get a 90 or above, then I get an A. You could look at it in reverse. If I did not get an A, then I did not get 90 or above. All right. So then if I confirm that I did not get an A, then I can assume that I did not get a 90 or above. All right. So applying modus tollens would be taking the, so I'll just kind of do it off on the side here. We have the S, then G. I have a not G. All right, that's over here in number 4. So therefore, not S by modus tollens. Now, all this side work, that's all for instructional purposes. If you understand this without doing the side work, that's fine. On the test, all I'm going to need are the explanations, the justifications, modus ponens, disjunctive inference, and so on. So that's why I was saying before that you're better off, or you're going to be more concerned with getting to know those laws, because that's going to, if you could fit the notation to one of the laws, then you have everything that you need. All right. Now, just looking at it very quickly, I have an S or L, and I have a not S. Well, if it's S or L and it's not S, well, then it's going to be L. So that makes sense for number 8. The rule that justifies that is disjunctive inference. All right. Yeah, it's an acquired taste, but the more you do, the more straightforward it'll seem. All right. I can tell you that it was kind of hard for me to follow early on when I was first learning this. But then I experienced more and more scenarios and ended up making a lot of sense out of it. I even got to the point where, and I apologize if I mentioned this already, I even got to the point where when my wife was studying for the law school admission test, the LSAT, there was a logical reasoning section on there that had little sentences. Now, they didn't say things like Michael likes math and Michael likes science, but they had little paragraphs that had a lot of conditional conjunctions, disjunctions in it. And I remember helping her by saying, all right, let's sit down, look at this and say, okay, that sentence, Tony is going to eat his breakfast if he had 8 hours of sleep. Sometimes they put the if after the then. So I would say, okay, let's let E represent 8 hours of sleep and B represent breakfast. So B, then E. And let's find something that'll help us break that apart. And through the logic of it, it was multiple choice question. Through the logic of it, we were able to come up with the appropriate solution. I make it sound easier than it was. It was definitely I don't want to say an ordeal, but it was, it took a little time and effort, but applying the logic really did help. Right. So that's an application, small application of it, or big, depending on what your career choice is. So I'm looking at this. I see I have a not A. The only places I see a not A are here and here. The loose premise that I have, the one that's not connected to anything, is the not D. All right. And so I see a not D here. I see a D here. it seems that I'm going to take the D or not A, if I really want to get started with the simplest thing, and apply the not D to that, just because everything else seems more complicated. Now, I have D or not A. Well, it's not D, so it must be not A. That's disjunctive inference. I had that extra statement there that shouldn't be there. It might be corrected on your notes. If it's not, then please make the correction. You could renumber it if you want. It's not a big deal. The numbers are just there so I have something to reference when I'm going through the problem, like take number 2 with number 5, that kind of thing. All right, so disjunctive inference, that justifies not A. So then I'm looking at it and seeing, all right, well, I used 3 and 4. Doesn't mean I can't use them again, but let's just put them aside for a second. The only other thing that involves a not A is number 1, so let's take that. Not A, then B, then not C. Let's put that together with the not A. All right. If I do not get a 90 or above, I'm using a not here because it has a not in there, then consequence. I did not get a 90 or above. Well, then I'm confirming that the consequence would be true. So B implies not C. That's modus ponens. Affirms by affirming. All right. Now, I don't see... Oh, no, actually, I do see. For the next one, we have not C, then A. Let me get a different color involved here. Not C, then A is right here. So it tells me I'm probably using the not D implies not C, then A. All right, so I want to use that because I want to be able to break off the not D. I'm going to use the not D again because this is a case where we're affirming by affirming. Affirm by affirming, which sounds weird. All right, so if this, then that. This, then that. All right, so we confirm the this, we get the that. Modus ponens. All right, B, then A. Well, I don't see anything in my set of premises that has a B, then an A in it, but I do see that I have, let me get a fresh new color here. B, then not C. These are now known to be true sentences. B, then not C. And then I have a not C, then A. If I drive to work, then I will not be late. If I am not late, then I will get a raise. So it would make sense to say that if I drive to work, then I will get a raise. Cut out the middleman. Anytime you're cutting out the middleman, you're talking about the law of syllogisms. All right? Some people call it the chain rule. If you're going from A to B and then B to C, aren't you really just going from A to C? That was my Syracuse to Buffalo to Toronto example earlier. The last one is I'm somehow going to get a not B out of all of this. And it's in these circumstances where it can be a little tricky because or you can assume that it's going to be something that'll work out, but it's just a question of how. So anything that is a true sentence is going to be helpful. And it may take a while to see this, but I encourage you to review this problem, try it again on your own. We know that B implies A is true. All right, we just proved that. B implies A is true. I need something to go with that that'll allow me to conclude not B. All right, and that's when you might even do a little guess and check. But if you know your laws, you'll look at it and say, well, the only one I can think of that'll allow me to negate the first part of a premise would be modus tollens. As long as I have a not A, that'll get the job done. And so it turns out we do have a not A. We drew that conclusion earlier. So this and that will give you the not B, and that would be by modus tollens. All right. So that's the lesson. Definitely take some time. I mean, really, none of this makes sense unless you have a pretty firm understanding of what's going on here. And you'll notice, I mean, just kind of looking at everything that I had highlighted previously on this page, aside from the law of disjunctive inference, which I'll highlight now, everything else, I mean, it didn't really work into it too much. Modus tollens also, I should say. We applied the law of double negation, but I mean, I could highlight it and I will, but that's kind of like, I don't want to say common sense, but people have experience with that, you know, just from like childhood. Like 2 negatives make a positive. I'm not going to try to do my homework, you know, like that kind of stuff. Commutative laws we touched on. These are the ones that seem to be coming back repeatedly. The stuff in the middle are also useful. Good general relations, like the identity laws. Those are pretty useful. I'm just looking. Absorption laws, you know, you can review those also, but the most popular ones are the ones I highlighted. Those are the ones that came up in these proofs. And again, like I mentioned before, for a test, I'm not going to be asking you to do a proof from top to bottom, like like you're given the premises and you have to come up with not only the reasons but the conclusions also. Not so much that, more so like what you see here.